Hello, Algebra 2 students. This is Miss Prater. I am going to be out of the office this morning. Today is Wednesday, October the 23rd. I'm going to be out of the office just for the first part of the day. So I did have to cancel class, and I am making a recording of the lesson that I would have taught, which is lesson 6.02. If we take a look at the two graphs, it says let's talk about the graphs, and I did a little research and I found two graphs that matched with the content in 6.02 that I thought was interesting. So on this first graph, anytime we look at a graph, it's important to look at what we're measuring on the axis, the x-axis and the y-axis. So on the x-axis, I have 0, 5, 10, 15, 20, and 25. And if I go up to the top, going left from right, it says we're measuring the daily new confirmed COVID-19 cases around the world. So 0 cases, and it says days after March the 1st, 2020. So 5 days after March the 1st, there are this many. If we go to the y-axis, this is daily new confirmed COVID-19 cases. So 10,000, 20,000, 30,000, and so forth on the y-axis. So 5 days after March the 1st, there looks to be about 5,000 cases. 10 days after March the 1st, 2020, there looks to be about 8,000. 15 days after March the 1st, there looks to be about 15,000. And then 20 days after March the 1st, it looks like there's about 30,000. And then 25 days after March the 1st, 2020, there looks to be, 62, 63,000. So I don't know if y'all remember when COVID hit, if you watched any news, they would have daily broadcasts where they were talking about the spread of COVID being very rapid, and it was increasing exponentially, and that we needed to do everything that we could to flatten the curve. So that was wear a mask, stay 6 feet apart. There were all kinds of things that they suggested in the beginning. Some were good, some maybe we didn't have to do. Still a big debate over that. But that's not the main thing we're talking about. We're talking about a situation that we know happened. Okay, so this is real data, where something increased drastically. And remember, one of the reasons that we needed to try to decrease or flatten the curve so the cases of COVID would not increase at a rapid rate was that when COVID first hit, it made a lot of people very, very, very sick, and they had to go to the hospitals, and then our hospitals were overcrowded and they couldn't take more patients, and then we didn't have enough breathing machines, and it just got crazy. So that's why they kept saying, please do these things. If you know you're sick, don't go around people. So this particular graph about daily confirmed COVID-19 cases is an example of exponential growth. So this is an example of exponential growth. And you're going to get so good at looking at these is as you look at the graph from left to right, you're seeing that it's increasing. So that's another way that you know that is growth. The second graph, if we look at the x-axis, is measuring mileage. We got 50,000, 100,000, 150,000, 200,000, and so forth. On the y-axis are percentages of initial price. So 20%, 40%, 60%, 80%. I found this graph because I thought it was interesting. And so there's different graphs. And I know this may be a little bit small for you, but the blue graph is Mercedes-Benz. The orange is an Audi. The yellow is a BMW. The green is a Volvo. The gray is a Volkswagen. The purple is a Ford. And then the dotted is just kind of what we call the exponential fit. We also call it a regression. It's basically like the average. Usually when I talk about this graph, somebody goes, how about the Chevy? Why didn't they put the Chevy in there? I don't know why they didn't put the Chevy. But what we're talking about is if you know somebody that goes out and buys a brand new car, The minute you drive it off the lot, let's say it was $30,000, the minute you drive any new car, no matter whether it's the most expensive car, when you drive that car off the lot and you start to put miles on it, the price of the car depreciates. It goes down. Cars are not something that typically hold a lot of value. The better the car, okay, the more expensive it is, probably in most situations to begin with, the better the engine, the better the body. It might hold its value a little bit more than a cheaper car. But in general, cars depreciate over time, specifically when they have a lot of miles on them. So if you're looking for a used vehicle, you're always looking for something that has low mileage. So this graph shows us, if we look at this, so this would be 0 miles on the car. So it has 0 miles on the car. The value of the car is 100% for all the makes and the models. Okay. When we get to 50,000 miles, the purple, okay, which is the Ford, it's worth about 50% of what it was. So that means if you bought that car for $30,000 and you drive it for 50,000 miles, it's worth half that. So now it's worth $15,000. The highest line kind of looks like the gray, the Volkswagen. Kind of looks like it comes up here higher than, oh wait, let me go to 5,000. Yeah, the gray and the blue look like the highest. So at 50,000, the Mercedes-Benz and the Volkswagen, if we go to right here, they're holding about 62% of their value. And then let's just say it was 30,000, 62% of 30,000. Let me pop that in my calculator. That means it's worth 18,600. So still quite a bit lower than what it was with 0 miles. And then as we get 100,000 miles, the percent of that initial value is totally decreasing. So this graph is an example of exponential, and we call it decay in mathematics, when something is decreasing over time. And it's decreasing rapidly. So when we say rapidly, that's the exponential part. It's rapidly growing in the COVID case. It's rapidly, exponential means rapidly, fastly. It's fastly decaying. All right. So our exit ticket is all about just looking at graphs, and it kind of goes more with the let's talk about graphs part. The rest of this lesson is going to be using some formulas. But just remember, this is growth, this is decay. If you want to take a picture of your exit ticket and email it to me, I will give you bonus points for it since we're not having class today. Totally up to you though. This week, Monday was a 5.10 unit review, 5.11 on Tuesday, part 1, part 2 for honors only. Wednesday is today. We're starting unit 6 with 6.02 with a quiz. Thursday, 6.03 with a quiz. Friday, and a catch-up day. Today's Algebra 2 objective we are covering is Course of Standard number 12, solve simple equations involving exponential radicals, logarithms, and trig functions. And we're specifically talking about the objective that deals with growth and decay word problems. So we're going to look at some word problems today. I promise they're not the hardest word problems you've ever done. In the email that I'm going to send this video link to you, I will also put the quizzes link. If you're somebody that's already gotten through 602 and you just wanted to practice some problems from 602 with some immediate feedback, you can also use the quizzes link that will be in the email. So number 1, let's review in the yellow box what an exponential equation is. An exponential equation is some type of equation, so it has to have an equal in it, and it has to have an exponent that is a variable. So y equals 4 to the second power would not be an exponential equation, but y equals 4 to the x power would. So for an equation to be an exponential equation, the variable has to be there has to be at least one variable in the exponent spot. Today we're going to talk about two equations. One of them is a growth equation. So when we read our word problem, we'll have to determine whether it's growth or decay. We're going to use this formula for growth. We're going to use this formula for decay. They are both exactly the same, except for growth has plus r and decay has minus r. So let's talk about the variables in the equation. A is the initial amount before measuring growth or decay. R is the rate of growth or decay. So one thing you have to remember is if they tell you that the growth rate is 5%, you have to remember to change that to a decimal. We don't use 5% in formulas. We have to change it to its decimal form, so don't forget to do that. And X is going to represent the time. Has it been 10 years? Has it been 5 years? Has it been 8 years? And then we just plug everything straight into the formula, and we're going to be solving for Y. Y could be money. Y could be number of cats. So it just depends on the problem. All right, let's look at problem number 1. The bear population increases at a rate of 2%. So keyword here, increases. And here's my rate. There are 1,573 bears this year. So what that means is my initial amount of bears is 1,573. My rate is 2%. We've got to remember to move the decimal 2 places to the left, and we're going to use 0.02 for our rate. I'm going to put an arrow going up, meaning increasing. It says write a function that models the bear population. How many bears will there be in 10 years? So we know we're going to use growth because the problem says increases. So we don't know, oh yeah, we do know X. X is going to be 10 years. So we're going to start by just writing our equation. So Y equals the initial number of bears, 1,573, and then it's going to be 1 plus 0.02 to the X, the number of years. Sometimes we know that straight up and we put 10 in. Sometimes we don't. We just leave the X there. And then we'll simplify what's inside the parentheses, and that'll give me 1.02 to the 10th, and then we will solve it. And then I just use my calculator in this step, and I do 1573 parentheses 1.02 parentheses to the 10th power, and for this one I got 1917.478. And then if we were talking about money, we could round it. We could take the 7 and round it up to an 8 to be 47 cents, but we're talking about bears. So we don't want 0.47 part of a bear. So we just drop. When it's something to do with something we need a whole number for, it doesn't matter whether the 4 rounds the 7 up or not. We just drop this because we don't want part of a bear. And we say 1,917 bears. So not too bad. I know that y'all definitely done some harder problems so far this year in Algebra 2. Let's take a look at number 2. A computer valued 6,500. So that means A is 6,500. Starts out being 6,500. It depreciates. That means it decays. It goes down. The value goes down at a rate of 14.3%. So my rate is going down. So I'm using decay. It's 14.3%. Remember to move the decimal 2 places to the left. So I'm going to use the decimal 0.143. And then A says, write an equation that models the value of the computer. And then B says, find the value of the computer after 3 years. So this is broken down into, so X is 3 years. So the A part, we're just going to write the equation, which means we're not going to put the 3 years in. Yeah, we're going to do that in the B part. So it's going to be Y equals initial amount times parentheses 1 plus 0.143. And in the A part, you're just going to leave the X there. That means you could put any number of years that you've owned the computer. So the A part just wants a function that represents the problem without putting in any years. So this is what they want for A. And then B wants to know what's the computer going to be worth after 3 years. So this is where you would put the 3 in for the X. And then you would put this in your calculator. And for this one, I got 4,091.248. And since this is money, then we know to round to the penny, which is the hundredths. So this would be that saying that the computer after 3 years, because it's depreciating, would be worth $4,091.25. I meant to mention this in the first example, but remember we started with 6,500. So if something is decaying or depreciating or declining, then you've got to make sure that this number is smaller. That's just a way for you to make sense with a problem. If we go back to number 1, remember we started with 1,573 bears. It said that the population of bears was increasing, so it makes sense that our final answer is more than our initial amount. So just in case you make a careless mistake, remember if it's increasing, your amount should be bigger than the initial amount. If it's decaying or depreciating, your amount should be smaller. Example 3 says in the year 2016, the estimated population of Canadian geese in a city was 750. So that's going to be our initial amount. I'm pretty sure the Canadian geese population is expected to grow. That means we're going to use the growth formula at a rate of 12%. So let's write down what we know so far. A is the beginning amount of the geese population, 750. The rate is increasing, so I'm going to do a little upwards arrow there just to help me remember, at a rate of 12%. Don't forget to change 12% to its decimal form by moving the decimal 2 places to the left. And then X is going to be the number of years. It says, what is the Canadian geese population in 2022? So you can't put 2022 in. You've got to put how many years have passed from 2016 to 2022. So you can do that in your head. If not, you'll do 2022 minus 2016, and that's going to give you 6 years. So in this problem, they don't just come out and tell you exactly how many years have passed. They make it a little bit harder for you, and you have to figure that out. The directions say round your answer to the nearest whole number. So we'll plug into our formula y equals A, the initial amount, which is 750. And then it's going to be 1. Our rate is increasing, so it's going to be plus 0.12 to the 6th power. 6 is the time. Simplify what's inside parentheses. I get 1.12. Put this in the calculator. And I got 1480.36. 1480.36. And they did say round to the nearest whole number, which is this 0. So we always look to the right. 3 is not 5 or more. So then we're going to round it to 1,480 and then make sure that you put what we're measuring, geese. So we started with 750. We're increasing to 1480. That makes sense. You would not want to get a number smaller than 750 if they told you that the rate was increasing. So really, we're just using the growth formula or the decay formula over and over again. I do think this is an easier section compared to some sections that y'all have already done. 4 is the last example. It says Alicia invested $32,000 in an account earning. Earning means making money, not losing money, 3%. She makes no other deposits. What is her balance after 7 years? So her initial amount in her account is $32,000. Her account is making money, so that's an increase at a rate of 3%. Don't forget to change 3% to a decimal. And she's going to leave the money in the account for 7 years. So X is your time. So again, this is growing, so we'll use this formula. Y equals initial amount, 32,000, 1 plus your rate as a decimal to the 7. You probably can plug this line in your calculator. I like to go ahead and simplify because I can do that without my calculator, and then this is what I usually put in my calculator. When I put all this in my calculator, I get 39,355.963. Since this is money, then I know I have to round to the penny, which is the hundredths place. So I look over to the right to the next digit. 3 is not 5 or more. So I'm going to round, I'm going to keep the 6. So my final answer is after 7 years, Alicia's going to have $39,355.96. And again, this should be more than what she started with because it was an increased problem. All right. Easy peasy. Hopefully, if you didn't already understand section 6.02, this will help. I'm also going to send along the whiteboard link if you want to save that. And then this is the exit ticket. So if you wanted to do this, this is just looking at 4 graphs, and then you're going to type or write growth or decay. And you can send it to me in an email and just say, hey, I watched your video today. This is the exit ticket, and then I'll give you bonus points for that. Have a nice day. If you have any questions, send me an email. Bye.